Welcome back, everyone. It's another day, and today we're going to be discussing one of my favorite concepts, memory. Now, some of you may have heard this word in relation to computers. For example, we've been using the word memory table as kind of this tool to help us understand and debug our code. However, memory is just a thing that we refer to of related to your ability to remember. Now, a computer's memory is exactly that. It's its way of representing how and what it wants to remember. So to go into this, the first thing that we all have to understand is computers are made of just ones and zeros. Everything your computer does is because a 1 turned into a 0 or a 0 turned into a 1. Every time you move the mouse, every time you press X on the browser window, every time you open a new tab, every time you play a game, all these things are just ones and zeros changing on your computer doing things. So the internet, which is all about multiple computers, are just sending ones and zeros between computers until they finally make sense to us. Now, this is really important because to understand memory, we have to go and understand how these ones and zeros relate to us. Now, last time, we talked about this concept of hexadecimal versus binary versus decimal. Well, it turns out that every single variable you have is really just made of what are called ones and zeros. Your computer program is just a bunch of ones and zeros. Your variables are just a bunch of ones and zeros. So for example, integers. When you say the variable int x equals 32. Well, in our case, we're clearly reading that x is a variable that is equal to 32. However, the computer actually has a memory table of its own where instead of storing the variable as the number 32, it's actually storing it as the number 32 but in base 2. So the computer is actually remembering that x is actually 0, 1, b, 1, 2, 3. So the computer is actually remembering that it's 0, b, 1, 0, 0, 0, 0. So when a computer stores a number in binary format, it stores it in what is called a bit. So a bit consists of exactly a single 1 or 0. So, for example, this number, 32, is comprised of 6 bits. It's a 6-bit number. And do you remember when we talked about variable sizes? It's been a while, but we should have been practicing it through our memory table. So an integer has a size of 4 bytes. 1 byte is actually equal to 8 bits. So 1 byte is actually something that represents 8 bits. And therefore, the biggest value a byte can have is, for example, is going to be all ones. So, and this number, because I've memorized it by now, represents the number 255. But when we come and discuss these concepts like bits and bytes, why are they really important? Well, just like a computer is made of a bunch of zeros, another way to say the same thing is that your computer is made up of a bunch of bits. Now, bits are extremely tedious to keep track of. And that's why the smallest unit that we'll ever talk about when referring to a computer's memory is going to be bytes. And that's the reason why every variable size is dependent on the number of bytes it has. So an integer is 4 bytes. A character is 1 byte. A short is 2 bytes. That's exactly it. So every single variable that we refer to is going to be referred to in byte format. So to count the number of bits a variable has, you just take the size, multiply it by 8 because there are 8 bits in 1 byte. Now that's going to be useful for you. So I want you to take that fact and put it away into your memory, and we'll come back to it in a little bit in this video. So now that we know that a computer is made up of a bunch of bytes put together, let's think about how it might work. So another key fact to remember is that these bytes are laid out in some sequential order. So a computer has a bunch of bytes, but you can think of it as a huge line of bytes that just goes from 0, 1, 2, 3, 4, 5, all the way up to millions. That's exactly why when you have a machine that has 4 gigabytes, a gigabyte really means 1 billion bytes. It's crazy to think about. Your computer, if you have a 4 gigabyte machine, is landing on the order of 4 billion bytes. Now, similarly, if you have an 8 gigabyte machine, so if you have 8 gigabytes of RAM, you have 8 billion bytes of RAM. Or some of you have a hard disk that's 1 terabyte. That is 1 trillion bytes on your disk. Isn't that an incredible amount of stuff to think about? So your computer has slots for each one of these. And whenever you make a variable, let's say of type int, what the computer does is it goes down a list and it says, okay, I'm going to take these 4 bytes and I'm going to use them to store the variable x. Bytes can be incredibly challenging to write. So 32 is a 6-bit number. Now, 6 bits, it would take, if I had 4 bytes, I would have to write out 32 lines and fill it out to represent x. However, remember, we use bytes. There's a shorthand way to write bytes. One of the easiest ways to write bytes are to convert the number into hexadecimal format. And if you remember, there's a quick way to do hexadecimal format for binary to hexadecimal. I can take each section of 4 and convert it out to 1 hexadecimal digit at a time. So the first 4 on the right become a 0, and the second one over here became a 2. So 32 can be written as 0x20. So now, the first 2 bytes of this integer are going to be 20. So I can fill out 20. And because I know the rest of the number is all zeros, I can just fill out 0 all the way down. So a computer, which is representing the int x with the value 32, is going to take 4 bytes and fill them out with the value 00000020. And now when the computer reads x or prints out x, it's going to print out the value of 32 for you. Now, the amazing part is the computer does all the magic for you, so we don't have to think about it in terms of binary. But it's still very useful to know. So now if the computer has occupied these first 4 bytes with the variable x, what happens when I say I want to make a new variable, int y, which is equal to 3? Well, 3 in hexadecimal can be written as 0x3 because it's just 3. The computer is going to say, I need space to make a new variable, and the next 4 bytes are the most logical place to put this. So it's going to go ahead and put the variable y right after the variable x, and it's going to fill it in. So it's going to be 00000003. So the variable y is taking up 4 bytes, which means it's taking up 32 bits, and every byte has 2 hexadecimal digits. So the very rightmost one for the variable y, which has the value 3, is going to be just 03, and the rest of them are going to be 0, is going to be occupied right after the variable x. This is important because whenever you have issues in your code, and pretty soon we're going to be covering a concept called pointers, so just a teaser out there, you're going to have to know exactly what part of the memory you're referring to. And if we get lost and we're not able to remember what part of the memory we're referring to, we're going to be confused. However, doing this by hand and drawing out byte tables like this is incredibly inefficient. It's going to take you forever to do something meaningful. So to go ahead, we're going to go ahead and take our tool, the memory table, and we're going to add a little bit to it. How are we going to add to it? Well, firstly, we're going to make a new column. And this column is going to be called the address of a variable. And don't be afraid, this is the last part of the memory table that we have to add. After this, our memory table is complete and there's no more information to add. Hooray! So, how does address work? Well, whenever you enter your code, the first place that everything is going to have is, it could be anywhere on the machine. And exactly how that is picked is actually really complicated. From now on, every time you either add a function or a variable into your memory table, you're going to have to also add an address to the memory table. Now, just like types, once the address of something is set, it can never change. The place in which functions and variables live, or their address in memory, is always going to be the same once it's set. So let's go ahead and take our code right over here. I'm going to go ahead and update it really fast to do something very, very meaningless. Int x is equal to 100, int y is equal to 50, int x equals minus equals y. Great, and then we're going to return 0. So the first thing we'll do in this code, just like any other code, is we're always going to start at the main function. The main function starts on line 3, and we're going to go ahead and write in main. The main function is of type int. It has no variable name. It has an undefined value so far, and the size of the main function is 4 because it's an int. Now, its address for the main function is always going to be, for now, let's use the variable a, because again, your program can start anywhere, specifically telling you the exact address requires a little bit more complicated steps that we haven't yet covered. So let's just always call this address A. Now, when we enter the scope on line 3, and then we're going to go on to line 4. Line 4 says make a new variable of type int, and this variable's name is going to be named x. The value of this variable is going to be 100, and the size of this variable is going to be 4 because it's an integer. Now, what is the address of this variable? So main is a function that started on A. So not only does it start on A, but because its size is 4, main occupies the next 4 blocks of memory. So now the question becomes, what is the next logical place for x to go? Well, x should go here. X should start going right after main. So main is finished at this point, and the question is, where does x go? Well, x goes right after main. So the best, we could call it where x goes B, but we actually know exactly where x is going to go if we know main is at A. X is going to go at A plus 4. Now, why is it at A plus 4? Well, main started at A, and then main takes up 4 spaces, or 4 bytes. So the next address that x goes to is going to be A plus 4, which is the end of main. And then additionally, we're going to occupy additional 4 blocks for x. Then we're going to go ahead and make a new variable, int y, which has the value of 50, and 4 as its size, because again, it's an integer. And where does y go? Well, just like x went right after a main, because that is the next available slot, y is going to go right after x. So y will be at a plus 4. So y will occupy the next 4 bytes of memory. And then we're going to change x by doing x minus equals y. So we'll take x and we'll subtract y from it and update the value of x. So that'll be 50. Now the key part here is all I can change about this variable is its value. I cannot change its name. I cannot change its type. I cannot change its size. I cannot change its address. None of this stuff can change. The only thing in your memory table that can change once you've defined it is the value. So now that we've actually changed the value of the variable x, not the main, not the address, not the size, not the name, not the type, we can now go on to the next step. And the next step says return 0. So return, finally we get to the part where we do it. Where when we made a scope thing, what we actually did in memory is we said we're going to draw a line as soon as we entered the scope. And we entered the scope right after main. Whenever we hit return, we're actually going to erase everything in memory up until that line. And that's exactly why in our memory table, we've been crossing things out. And then I'm going to set the value of the thing that's right before the line, so in this case, A, to be a value of 0. And now that's why main gets the value of 0. And then I'm going to go ahead and finally give back, the computer is going to go ahead and read the last part of my code, which is where main started, and give me back the value of 0. That's what a memory table is doing in this case. It's not trying to be complicated. It's actually quite simple. It's really just adding one more concept to help us slightly more deeply understand what is going on in our memory table and why we cross things out like we do. So now let's say we have another memory table. This time I'm going to use variables of different types. So let's say y is a short, and I have another variable after this called, and actually I'll do one more thing. I'll actually give us a function that we're going to use. And this function will return a car, get letter, and car letter, and stood cn letter, return letter. So now let's talk about how functions are going to relate to the memory address. Now, this is not going to be any more complicated than last time. We're just going to build our memory table like we're used to doing. The memory address is just giving us one more level of understanding. So if we get confused, we have another way to cross-check and validate what we're doing. But for now, it's just a way for us to more deeply understand what we already know. So once again, let's get started. We're going to enter the main function. The main function is going to be of type int. It has no variable name. It has an unknown value. It has a size of 4 because it's an int. And the address is going to be, again, be A because our main function will always just start at A. So the first 4 bytes are occupied by main. And then we're going to enter a scope on line 9. And then we're going to go ahead and make a new variable called int x. The value of this variable is going to be 100. The size will be 4. And where the variable x will begin will be 4 bytes because that's the size of it. And it'll begin at a plus 4 since that's the next available slot. So let's write x over here. And then we're going to make a new variable of type short y 50. The size is 2 because shorts are 2 bytes. Where does y begin? Well, y is passed on right afterwards. And where does y begin? Well, y begins relative from a. It's just 4 more from x. So it'll be x plus 4, since that's where the next available slot is in our memory. And then we're going to go ahead and update the value of x to be 50 because we're subtracting y from it. And then we're going to go ahead and do line 15. Well, line 15 does a couple of things. The first thing line 15 does, it says make a new variable of type char called myLetter. The value of this variable so far is unknown. The size is going to be a 1 because it's a single byte. And this variable is going to go right over here, which is myLetter. But unlike everything else, it's 1 byte. So where does this belong? Well, we know that this was a plus 4. Specifically, this first one was a plus 4. This first one was a. This next one was a plus 8. Where's this one? Well, this is going to be 2 more from a plus 8, which is going to give us a plus 10. So let's go ahead and write that in. And then we're going to enter a function. Our function is going to be named getLetter. GetLetter is of type character. It has no variable name. It has an unknown value so far. The size is 1 because a character has a size of 1. So where does that go? Well, that goes right over here. And that next one is going to be a plus 11 because that's the next available slot. And let's name this one getLetter. And then we're going to enter a scope on line 3. So let's mark that over here. And then we're going to make another character called letter. Its value is unknown. Its size is 1. And let's say now that where's the next slot that it goes to? Well, it turns out that the next slot is going to be 1 right afterwards as well. And this one is going to be a plus 12. So we're going to go ahead and fill that in. We're going to go ahead and do a user input of stdcin or console input into the variable letter. Well, let's say the user entered in the letter v. Well, in that case, the value of the letter would be variable v. And then line 6 says return letter. So what do we do with return? Well, return says the first thing we do is we fill out everything. We fill out the result of this variable in the result of the function. So this gets updated to the value of v. And we erase everything all the way up until that line. So this memory gets removed. Now what happens next? Well, the next thing that happens is that the variable when we hop back to line 15 says the value of my letter will read whatever the next available chunk of memory is. And that happens to be, and by definition, is the thing that the function is giving back to us. And that's exactly why my letter also becomes v. Our computer says we're done with this as well. And then we're going to hop back over and we're going to do the last part, which says return 0. So return 0 is going to do what we just did, which is set the value of our function to be 0. And then it's going to, oops, I forgot to cross things out. And then it's going to go ahead and say, I'm going to go ahead and erase all of the memory for everything that was built up until the last scope. Boom, gone. And we're going to cross these out as well. And then I'll return whatever the last variable is, which is main, which has the value of 0. Now let's imagine that in my code I just added some scope. So let's take this third example, for example. I'm going to go ahead and write the memory table for this, and I'm going to fast forward through some of these lines to make it slightly faster. So we have the main function. The main has a type of int. It has no name. It has an unknown value, size of 4, starts at A. We're going to enter a scope. On line 3, we're going to have a variable of type int named x with a value of 100, size of 4, A plus 4 is its address because that's the next place. And then when we enter another scope, on line 6, we're going to make a new variable, int y. This y will have a value of 50. It is a size of 2, and additionally, the address is going to be A plus 8. Now, what do I do on line 7? Subtract y from x. So I'm going to update the value of x to be 50, and then I'm going to exit scope. So let's just really quickly draw our chunks of memory out before we get too into it. So this is the main, which starts off at A. We then entered scope right over here, which then led us to main at x, which starts off at A plus 4. Then we entered another scope and made y, and y starts at A plus 8. And then we actually exited scope. Well, in this case, what does that mean? We have to delete everything all the way up until the last scope that we have available. So we have to just delete y. And because it's on a function call, we don't actually use the value, so the line is just reminding us where we're going to delete until. So let's go ahead and quickly cross this out from our memory table. And then we're going to go to the next line. The next line is going to say short z is equal to who knows what. The size is 4, and again, z is going to be right over here with 2 bytes, and it's going to be A plus 8 again, because that's where the next available slot of memory is. So what would z be? Well, let's try. Let's try really fast. Well, in this case, z is 3,765, which doesn't make sense because just a few minutes ago, we had the same place in the same memory where we had stored the value of 50 into the value of A plus 8. So when we went to A plus 8 again right afterwards, it should have had the value of 50 because that's how memory works. It's not like the computer made new memory. All it said was its memory location A plus 8 now refers to the variable of z. It didn't make a new A plus 8, it already had an A plus 8 location in memory. So I think the really interesting question to ask here is, why did it not do what you wanted? Well, it turns out our modern computers are actually much more sophisticated than the model we're representing in the memory table. Now, we'd expect that z would have the same value as y. So why is it not exactly the same? Well, it turns out that your computer and the C++ language is doing a whole lot more to kind of change your code a little bit behind the scenes. Now, not in a bad way. Your code is still doing almost exactly what you told it to do. However, there are some parts of it that it's simplifying and making easier for the computer to understand, and sometimes it even skips steps. It's very hard to actually say exactly what the computer is doing, but this memory table gives us a rough idea of what can happen. Now, it makes no promises that this is exactly going to be replicated. Sometimes you'll have a bug that in your memory table, but not happening on the computer, or the vice versa. And often the reason that will happen is because you'll be doing what's called undefined behavior. So when we're printing out the value of z, which is a question mark, and in our simplistic model of the memory table, at memory location A plus 8, we had the value of 50 not too long ago. And if we don't change the value of that memory, the memory should remember that it's still 50. So in our memory table, we would have technically printed out 50. However, in the computer's case, it's printing out 32,765. Well, that's because the question mark means undefined behavior. If you do undefined behavior, your results are undefined. And that's exactly what's tricky about this sort of stuff. So sometimes when you have a bug, one of the easiest things to look for are things like undefined behavior. That's because, again, the computer's memory and what it's doing is a very complicated concept. We can understand the basics of it, but predicting everything that the language is going to do under the hood for you is virtually impossible. All we can have is a good idea and a mental model for what it's doing. And another part that we could really go about learning about this is thinking about why do we want to use different types. For example, let's say I have the variable x. Well, in this case, the variable x is taking up 4 whole bytes. It's taking up double the memory that my variable z or y took up. And if x only has a value of 100, perhaps I should use the smallest type that I can to represent it so as to not waste memory. Have you ever wondered why apps like Chrome or Slack take up gigabytes of memory? When we write software, it's important that we think about the end user. Whenever we think about the end user, there are many constraints. Sometimes it's thinking about making sure that their code runs fast on their machine. We also don't want our code to consume all the memory of their machine. And right now, we're writing very small programs that aren't really consuming that much memory yet. We will get to programs that are consuming tons of memory coming up. However, for now, our programs are fairly constrained. So when you write your memory tables and you write the address column from now on, you probably won't get that far in. You maybe get to 100. At maximum, 200. I don't see the examples that we've been doing up until now taking up more than that much memory. However, as we get to expand to more and more complicated topics, we will get to programs that take a lot of memory. For example, writing a browser, writing the YouTube app. All of these apps consume tons of memory. So hopefully, as we get better and more involved into writing more complicated software, with this new insight, this is something you'll consider whenever you're writing code. Perhaps you'll use the best type of variable. Perhaps you'll, at the very least, think about the end user experience and how your usage of memory can affect how fast their computer is or how fast their app is. Perhaps even how much battery life their app is going to take. So with this, I'm going to leave you off and hopefully go towards where you can go ahead and write some of these memory tables using the new address concept we learned. And next time, we're going to be discussing a thing that really builds off of this, which is pointers. Until then, adios.